This is to document my journey from coming up with the idea for a walking robot through designing, wiring, coding, and finally realizing a working leg for a quadruped. Ultimately, this project ended up being amazing practice for a wide variety of different areas within robotics, which is perfect because the 5 main topics I'm going to cover in this video are foundational for understanding more complex robotics. We can move on to the next topic, which I'm titling Prototyping. It's going to cover research, ordering parts, and making a rudimentary first version 3D model. First, I spent some time researching other projects on YouTube and Instructables. I ended up ordering inexpensive 35 kilogram servos for the muscles of the leg, some bearings for the joints, and some other sensors and radios that I'll get into later. Down the line, once I have everything assembled and tested, I'll design and order a custom PCB from the sponsor of this video, PCB. With the electronics ordered, I know the dimensions of the servos, and I can start prototyping the leg. I've started doing a rough, I'd almost call it sketching stage, where I create a rough 3D model with zero intention of ever printing it, just to wrap my head around what I'm making. I ignore all the normal rules of 3D modeling. I'm just trying to create a general design as fast as possible. With the rough 3D model sketch done, I can move on to the second topic, 3D modeling and mechanics. First, I'll create parameters for all the dimensions of my parts. Then, I'll create an assembly sketch to locate the joints, and a top sketch to define the first joint and the width of the femur. After designing the connector between the first 2 servos, which I'm calling the hip, then I can create the first side of the femur, add some details, then mirror it across. To model the end of the leg, what I'm calling the tibia, I create an interface onto the servo, define where the tip of the foot is and create some arcs to connect it, then add some more details like the supports. I'll extrude the main part of the tibia, then define and extrude the foot. With the design almost complete, I'll add some holes for the screws and bearings, and add some other details. And I'm done. Next, I can go ahead and print the parts. I'll just arrange them on the bed, preview, and print. I just had to clean up the brim. Then I'll use this tool on the soldering iron to add threaded inserts to the parts, and then just put the servo mount together. Now that I know my design fits with the servo, I can put together the second part of the leg, the femur. With the servo mount assembled for the new joint, I can attach the horn and screw the legs together. Then, the horn side of the femur attaches to the second servo, and the bearing side of the femur attaches to the other side. Before going any further, I want to plug the servos in and test that the design works so far, so I'll use an Arduino and buck converter. And wrote a quick script just to move the joints through their range. The femur assembly is working great, so I can move on to the last component, the tibia. With more cleaning up the pieces and threaded inserts, the other end of the femur gets a metal horn. Then the third and final servo is fitted with a mount and attached to the femur. Then the 2 sides of the tibia are attached with the axle for the ball bearing. Then, the other side of the femur needs a bearing as well and gets assembled. Last, we've just got to attach the toe piece of the tibia. Now we can reattach the leg to the weight and test it out. It's time to cover the next and, in my opinion, the most stressful topic, electronic prototyping. Now I'm going to make a slightly more official prototyping board. This is just for controlling the servos, so I'll only need some jumpers, capacitor, pin headers, and wires from the smart faucet. I'll solder the pin headers onto the board, then add shared wires for power and ground. Then I'll add jumpers for each of the 3 servos control pins, and add a capacitor between the ground and power. I can plug it into the buck converter, plug the jumpers into the Uno, and connect the servos. Now it's time to test it out. I already tested just the femur with a really simple script, so to make this next part meaningful and before finishing the electronics, we're going to need a better control method, bringing us to another topic, inverse kinematics, or IK. There's probably thousands of videos about IK, so I'm not going to go too deep. In one sentence, IK cares about where the tip of the leg is and figures out the angles of the joints. When I was first looking into this for my robot, thinking about this in 3 dimensions felt impossible, until I realized an easy shortcut. Just picture the situation. There's a goal point and 3 joint angles to calculate. The first joint always has an axis perpendicular to the other joints. That's the only joint that can really control forward or backward movement. So the shortcut is, just using the x and y coordinates, I can calculate the first joint. Then, with the first angle solved, I can do the rest of the geometry on the vertical plane running along the arm, making it a 2D problem. I can just follow this literal textbook example of inverse kinematics in 2 dimensions. We'll actually calculate the third joint next, leaving the second for last. Here's another trick. The third joint is what controls the distance between the second joint and the goal, and we can easily figure out that distance. Then, we figure out the joint angle to achieve that distance, and the third joint is solved. Finally, we've just got to solve the second joint angle. In the last step, we use the distance between the second joint and the goal. In this step, maybe intuitively, the second joint controls the angle between itself and the goal. We just have to figure out the difference between the current angle and the goal angle. And then we're done. Now I just have to write the code to actually implement this, and also write a really quick React UI to control the leg. In the UI, I can click on either the side or top view to set the goal point. It sends the goal point to the microcontroller, then the IK algorithm runs on the controller and solves the joint angles. The controller moves the servos and sends the angles back to the UI to display the intended leg position. After getting everything wired, I uploaded the code. Back to the electronics, this robot isn't just going to be an Arduino and 3 servos. There's going to be some transceivers and sensors required to control it and exchange information. There's an NRF chip for radio communication, a Bluetooth module for easy connection with a phone or computer, and I also wanted an IMU, like a gyroscope, to sense the orientation of the robot. As the brain of it all, I'm going to use the Arduino Mega Pro. I settled on this because I'm comfortable with Arduino, it has a small form factor, it has 5-volt logic, which is the same as the servos, and it has plenty of GPIO pins. To make sure it's reasonable to wire all of this up, I'm going to make a schematic first. All of these modules have to be connected to particular pins on the Mega, not just any GPIO. The Bluetooth has to be connected to serial pins, the radio uses standard SPI pins, and the IMU uses I2C data transfer. Now that I've eaten all my metaphorical vegetables, I can design the PCB. I have to make sure all the parts in the schematic are linked to footprints, design some custom ones for the NRF and servo connections, and then import everything. Now, I just gotta figure out how to fit all these pieces. There's terminals for the power and on-off switch, 4 sets of pins to control the leg servos, the NRF radio, the Bluetooth module, and the IMU gyroscope, which I want to keep in the dead center of the PCB. To conserve space, I'll put the microcontroller on the back of the PCB. Then, I gotta wire everything together. I'll also add some grounded mounting holes. And last, but certainly not least, some silkscreen designs. It's time to export Gerber and drill files, then upload to PCBWay. It'll automatically read the dimensions and layer number from the file. And it even shows a rendering of the PCB, so I know I uploaded the right thing. Then I just place the order. The PCB looks great, and I need to cut and solder the pin headers, the power terminals, and the servo capacitor. With the bare bone pieces assembled, I'll connect the barrel jack and on switch. Then finally attach the controller. I designed another piece for mounting and screwed on the PCB. Then the leg is fastened to the mount with a couple screws. Next, I'll plug in the motors, link the controller to my computer, and connect the power. I forgot the leg will immediately move to the initial state when it started, so I flipped the power switch and it surprised me that the leg jumped. I'm showing the UI on the bottom corner of the screen. To my happy surprise, it seemed to be responding to all of my commands. In some final performance testing for the whole design, I'm surprised how fast and accurately it can move. In my next video, I'm going to make many improvements on the leg, and I'll actually get it moving around. Thanks for watching.